Okay, we're going to talk about mixture designs. Last year, we talked about fractional factorials, response surfaces. And this year, we're going to pick up mixture designs. Now, if you're doing plant tissue culture and you're making media, these are mixtures. So the mixture set is a really important tool in the DOE tool set for those who are doing plant tissue culture. Okay. Now mixtures, what I'm going to do, I'm going to cover in the 30 minutes, I'm going to cover the concepts of mixture designs. They're very, very different than anything you've ever seen. If you've never been exposed to mixture DOE, you're in for a real treat, okay? That the concepts are fascinating, it's really different, okay? And you don't see a lot of it in the literature, but it's very relevant to the kinds of things that we do. Now, it looks like there's a problem finding, hope they didn't lose my presentation. It says needs on it. There it is. Very good. Very good. Okay. All right. Mixture designs it is. Yeah, so we really can't talk about DOE without mixtures. And mixtures are so relevant to the in vitro community, we have to talk about them. So what I'm going to go through is what is a mixture, and everything, remember, I'm going to be talking about is all in the context of DOE. There's a lot of language that's used just, we just use in common life, but we have very specific definitions in DOE for mixtures. We're going to define what a mixture is. What does a mixture experiment look like? What is a mixture effect? Very different from what we're used to. And how to combine mixture and non-mixture factors. In fact, it's number 4. This is probably the type of experiment that you're going to be running if you find that you need mixtures in your work. And then I have a couple examples, so you can a couple things I think where mixtures are particularly relevant in plant tissue culture. So the very high-level definition of a mixture, Cornell and People, these are 2 major contributors, statisticians in the mixture design literature, is they're simply combinations of ingredients or components, which is that's the statistical term for the ingredients in a mixture. They're called components. I'm going to talk about that later. And these are combined, and the resulting product is something that has useful properties. The key idea on mixtures is that the response is a function of proportions, not amounts. And I'm going to hit this pretty hard because we are very, very sensitive to this. I went through years to wrap my head around mixtures, to become comfortable with thinking in that framework. It's a function of proportions. Now, sometimes you'll have a situation, and it's not really clear if what we're dealing with is a mixture. And Pat Whitcomb, one of the founders of StatE, says, one question you can ask to help answer the question is, you say, if I double everything, will I get a different result? If the answer is yes, you're not dealing with a mixture, okay? Mixtures are proportion. And I'm going to show you, okay, so here we have some mixtures. This is where only proportion matters. Okay, and again, I'm going to emphasize the response is a function of proportion, not amount. So here we have a nice bowl. It's a really nice trail mix. And imagine that you're going to research and you want to develop the ideal trail mix. And you have all the individual components that make up this trail mix. You have the cashews and the cranberries, et cetera. Okay. You say, well, am I dealing with a mixture? Well, if we use Pat's definition, if you double everything, if you double the size of that bowl, is that going to taste any different? Well, no, it's not. That's a mixture. Okay, mixtures are formulations that are composed of two or more components. And you're going to hear the word components, not factors. The word factors does not apply to mixtures. They only apply to quote, factors that are independent, and we'll talk about this. So because they're proportions, no matter how many components you have in your mixture, the sum of the components is going to equal 1. So what is a mixture experiment then? Well, it's where we vary the component proportions, not the amounts. And the experiment is going to determine the effect of proportion. Again, not amount. Amount is fixed. So when you're varying the proportion, the amount will be fixed. Again, amount plays no role. So what does this look like? Okay, here's two components, A and B, and we want to run an experiment. And so one of the treatments is 25% A in the glass. I just measured the height of the glass, this is not volume. As soon as we specify what proportion of the glass is A, B now is defined. It's not independent. So B is 75%. And so this is what we mean that components are not independent. So last year, when we dealt with the fractional factorials, the RSMs, these are all independent factors. Mixtures are not. Okay, now I'm going to explain what happens with mixtures. And I'm going to use the geometric approach. I really like this approach. It's helped me a lot to understand conceptually what's going on. So whenever you set up an experiment, there's always an underlying geometry, okay? And some of you have heard me talk about this. Whether you know it or not, it's there. So, for example, and the rule is for every factor in your experiment, that equates to a geometric dimension. So a one-factor experiment, one-dimensional geometry align, as you see here. And then we vary that factor from some low level to some high level. We measure something, and typically we're measuring a lot of things, and then we can plot the function of our response over our design space. Two factors, two dimensions, a plane. It's very intuitive. We sample the plane. This is what DOE does. This is what your software is doing. It has the algorithms to sample that space. Three factors, three dimensions, a cube. Okay, and you can see how this works. And we can keep going up in the dimensionality of our design space. Four factors, that's a hypercube. Okay, and 5, 6, 7, 8, there's a design space that's going to be sampled to determine how the response varies through that space. Now, these are all for factors that can be independently varied. Now, the factorials, the response surfaces, these are all factorial type experiments, all factors that are treated independently. You cannot use factorial type experiments with mixtures, and I'm going to show you why. It's pretty neat. Okay. First, factorials confound the effects of proportion and amount. I'm going to show you what this looks like. And second, factorials sample the design space poorly. And what I should have written here is the mixture design space is sampled poorly by the factorial type designs. And I'm going to show you what that looks like. Okay, and we're going to use lemonade. We're going to develop the ultimate wonderful tasting lemonade. I work in the citrus industry, though actually I think I heard Statistical use this example years ago, and it was a good one. So we're going to set up a factorial, okay, 2x2 factorial with lemons, 1 and 2 lemons, and 1 and 2 glasses of sugar water. Okay, our factorial will generate the 4 treatment combinations, but watch what happens. Okay, so if we look at the proportional relationships between lemons and sugar water, this is what you have. And notice here, for the proportions, that those two treatments, which the factorial sees as two separate treatments, from the mixture perspective, that is only one treatment. Likewise, if we look at amount, and now we're simply summing the lemons, or lemon juice, and the sugar water, the factorial sees two separate treatments, but they're the same from amount. Okay, so here's the design space of a mixture. And the geometry rule for mixtures is you take the number of components and you subtract one. Remember, if they're independent, it's simply the dimensionality of the geometry is just the number of factors. One factor a line, two factor a plane, three factor a cube. For a mixture, it's the number of components minus one. So here we have two components. We have the lemons, we have the sugar water, minus one dimension. That's a line. But we have to fit two components on the line, and there's your ratio. Now you'll notice at the extremes of the line, we have 100% sugar water and 100% lemon juice. Okay, that is a mixture. And in the statistical literature on mixtures, they are called the pure blends. They're pure blends. It's just one component. So the mixture is 100% of that component. Okay. So here what we're doing, I just plotted the proportions from the factorial onto the mixture design space. You see how terrible it is, okay? It samples it poorly. And I can tell you, like even with RSM where they're independent, we're only talking about one dimension now, a line. I can tell you as your experiment, as the number of factors or components increases, this problem of poor sampling is going to get worse. Okay, now here's where it gets interesting. Mixture effects. And there's some really good examples in metallurgy on this, and I'm going to give you one. It's one that that Mark Anderson wrote in this book, Formulations Simplified. This is StatEase. If this is worth getting, okay, if you want to learn about mixtures. Mark is a chemical engineer by training, so he's not a statistician. So he writes very clear, very useful. Okay, very good book. Okay, so he talked about, he was at a museum, and they had an exhibit of ancient Greek artifacts, including jewelry. And so he said the jewelry, he said it was amazing. Now Mark is a chemical engineer. He was really interested in the alloys that they use. So he looked it up. Well, it turned out that these ancient Greek goldsmiths used a mixture of gold and copper for their solder. Well, it turns out, and the reason they did that is because the mixture of gold and copper has a lower melting temperature than gold or copper separately, okay? It's a pure mixture. And so I dug up, I put this together. So here's the gold-copper melting temperature phase diagram. So everything above the line is liquid, and everything below the line is solid. And you'll notice down along the x-axis there is our mixture, okay? Ranging from the two pure blends, so the pure blend of gold, 100% gold on the left, and you see that gold melts at 1,043 centigrade, and then on the far right is copper, the pure blend of copper, and it melts at 1,072. But something interesting happens as you start to blend copper and gold. You get this relationship that bottoms out at 923. So the ancient goldsmiths would mix roughly around 47% copper, 53% gold, and that's what they used as their solder to make the jewelry. Okay, so what I'm going to do here, I'm going to strip off all the details, and we just want to get into the concept. So imagine, and what we have here, we got a mixture of A and B, okay, from pure blend to pure blend. And let's say you run an experiment like this, and your data is a line, okay? Since that's a mixture, and we're varying only the proportions, the effect that you're seeing is what's called linear blending. So in the analysis of variance, there's going to be a linear blending term. And what it's going to tell you is the difference between the two pure blends, okay, in terms of linear blending. Now, you may see something else, and it could look like this. You can have deviation from linear blending, either above or below, and this is called nonlinear blending. And this is what mixture designs can detect. Okay, the factorials can't really detect this, and the mixture designs can detect it and model it. And in your analysis of variance, I'm not going to get into analysis of variance. It's more important to understand the concepts. There will be there'll be more than one, but there'll be nonlinear blending terms, and you'll actually see, okay, if your mixture is having an effect like this. Okay, back to our phase diagram. So it's very clear here, if we only had linear blending, you would have the blue line at the top, but what's actually observed is this very nice nonlinear blending. So as soon as you see nonlinear blending, it raises the question, is this a synergy or an antagonism? Now, in the DOE literature, synergy and antagonism they have a very specific definition, okay? And they refer specifically to nonlinear blending. So if you were to come to me and you say, hey, I ran this experiment, and we got a strong nonlinear blending on whatever, what I would ask you, is it a synergy or an antagonism? Okay? That will tell me how useful the blending is to you. Okay, now let's go back to our phase diagram, okay? And I'll put a question to you. Okay, so what the ancient Greeks observed here in their solder, is that a synergy or an antagonism? So raise your hand if you think it's a synergy. Okay? Raise your hand if you think it's an antagonism. Okay? Well, that's a big club. I don't know a lot of stuff. When you're doing DOE, we're all practitioners. We're all learning. Okay, I'm going to give you a hint. Okay, synergy has a positive aspect to it, and antagonism has a negative aspect to it. Now think about what you were thinking. See if you change how you look at it or keep it the same. The answer is, this is a synergy. And the way it's defined, synergy and antagonisms are defined based on what it is the experimenter wants. So if you're an ancient Greek goldsmith and you're developing solder, you want a lower temperature. That's a good thing. So therefore, it's a synergy. I actually got in an argument with a reviewer. We went back and forth because I used this. The reviewer absolutely did not believe there wasn't an objective. Well, there is an objective definition, but it's up, okay? So finally, I actually had a copy out, literally had a photograph out of a stat book, the definition, and send it to the reviewer, and then the paper was accepted. So this is pretty neat. The synergy is usefulness, okay? So in this case, usefulness is minimizing. That's the synergy. Okay. Now, how to combine mixture and non-mixture effects. And I can tell you, if you do a mixture experimentation, it's probably going to be this type. You're probably not going to deal with pure mixtures like lemonade or trail mixes or anything. You're going to be doing this, and I'm going to show you why. So here's fertilizer, and a lot of different fertilizers out there, but the one thing they all have are these three numbers, and that's the NPK ratios. It's understood that proportion matters with fertilizer, but if we put too much fertilizer on our plants, we're going to burn them or even kill them. And so amount matters, and it matters big time. So we have proportion and we have amount. So how do we combine the two? Okay. So we're going to go back to the geometry. And here we have, as you remember, this is a one factor, one dimension. There's our line. Here's our mixture design space. Remember, the mixture geometry is the number of components minus one. Okay, and so this is, so with two components, it's the ratios. And I'm going to switch it to something a little more relevant. Okay, the ammonium nitrate ratio. Okay, in your cultures. Okay, this is a big one. Okay, so here's what the design space would look like. Okay, now let's talk about how do we bring in amount? Now remember the rule, we're bringing in amount, it's a factor. Okay, we add a factor, that means we're adding a dimension. So we have to add a dimension. So let's add it. There it is. So we have amount, which is the total millimole of ammonium plus nitrate, and then along the bottom axis is our mixture component. And the design space is a plane. But what we've done is we've separated the effects of proportion from the effects of amount. Okay, and the way you read this is there's a point there, 21 millimole total. And the ratio is 25% nitrate, 75% ammonium. And so the actual formulation in our treatment is going to be 5.25 millimole nitrate, 15.75 millimole ammonium at that point, and likewise through the rest of the design space. So your DOE will select the points, you'll sample it, but it'll be done this way. Okay, now remember, factorials confound the effects of proportion and amount, and we saw that earlier, where the factorial sees two treatments, the proportion mixture sees only one. The same thing happens if we treat something that's a mixture, okay, independent. So here's what the design space looks like if we were to experiment with ammonium and nitrate and treat them as independent factors. We are going to confound the effects of proportion and amount. Now here, we've separated them. So here, we're going to know exactly what's going on. But this is really the cool thing. Oh, here, let me show you how this, so here, some of the properties of this. So if we take the ratio, we'll take there a 75%, and we push that through across the amount dimension, every point on that line is 25%, 75%. It does not vary. It only varies on amount. Likewise, if we go the other way, so at 21 millimole, and we push that across the proportion dimension, amount is fixed, but the proportions are changing. This is beautiful. So your analysis of variance can now pull out everything separate. It'll be very clean. And it's even better than that, because they're both planes. I can tell you it's the same number of treatment points. Now, where would you want to do your work? Which one do you want to use? The one on the left is going to give you so much more information. It's not like you're not going to get any information from the one on the right, but to use the appropriate structure, you're going to get a lot of information, and it's not going to cost you any more work. Okay, I'm going to give you an example here. I just want to push it up a little bit. So let's add another component, throw in K. K is another big one in there. Okay, and again, remember the rule, we have number of components minus 1. So 3 minus 1 is 2. That's a 2-dimensional geometry. 2-dimensional geometry for 3 components is the triangle. So what you'll find is that mixtures have it's like a triangle base. So as you go up in dimensionality, triangle, tetrahedron, hypertetrahedron, these are all hypertetrahedrons all the way up, unlike the square, the cube, the hypercube. Okay, now, mixture amount. So, and the way you read these, the points as all coordinates in a mixture space sum to 1. So you'll notice the geometric center, a third, a third, a third. The vertices are pure blends, 1, and likewise. So anywhere in that triangle, the proportions will sum to 1. But remember, we want to run a mixture amount. So what we need to do, we're like you saw earlier, amount is a factor. So a factor is going to add a dimension. So we're going to have to push our mixture space through an amount dimension. Can you get that? I'm going to show it to you. It's kind of cool. I love these kind of experiments. Okay, so that's what you're doing. That's your experiment. So each triangle is your mixture design space, but each triangle, because it's pushed through amount, the amount is different. Okay, and if you think about this, you might start to see that. If you think about it some more, that. It's a triangular prism. So this experiment is a triangular prism, and then what your DOE software is doing, it's selecting points to sample the space within that prism. Okay. So here's a paper here we published a number of years ago that explains how to structure. If you want to know the effect, if you want to know the effect, what ratio should I set my cultures at? How should I set the ammonium nitrate ratio in my media and the amount of nitrogen? This is the design to do that. It's universal, okay? And because nitrogen is such a big player in the media, this is easy to run. This is like money on the floor for you to pick up, okay? It's all done. This is a really beautiful design. So when we ran it, these are embryogenic lines from citrus. And again, you can see the ratio along the bottom, okay, and then the amount. Now, it's structured in a sort of a weird way. I'd have to explain it, but it's a standard mixture amount. This is going to tell you how much nitrogen to add and what ratio should you use. Now, what we were using was MS, and there's the MS point right there. So it was a dramatic improvement in growth, very easy to identify. Okay, so for the nitrogen, the ammonium nitrate ratio and nitrogen, the mixture design, that's the way to go. The other area is growth regulators. So here's a paper here, mixture screening. Now, mixture screening, if you have a lot of components and you want to just identify the ones with the largest effects, that's a mixture screening design. And then the mixture amount, everything I've talked to you about is in here. A lot of the concepts are explained in here. But this one, I think I took 6 cytokinins. We did a mixture screening. BA and zeatin riboside were the most active for our citrus cultures. IA and NAA were included because they were universally the ones everybody was using in citrus. So I thought, okay, well, let's make a mixture of those 4. 4 components, minus 1 is 3. That's a 3-dimensional geometry. That's the tetrahedron. And then we want to look at amount, because amount matters with the growth regulators. And so we're going to push that tetrahedron through the amount dimension. That's in the paper. Actually, the reviewers really like that figure. They said, that's pretty neat. Yeah, it is neat. Okay. So that's the experiment. We had an amazing diversity of type morphologies. We had things with an enormous number of shoots, single shoots, no shoots, different callus morphologies, et cetera. And the beautiful thing is now we can quantify and we can tell you exactly why they are acting the way they're acting. And to me, this is what the DOE brings to the in vitro community. We see all the really cool stuff that's being done in genomics, okay, in molecular biology. The counterpart to that is for us who are folks who are growing things to actually understand what's doing what, and that's the DOE. And you marry the two, and it's really, really wonderful. I think that's it. So I will turn it back to, I guess we'll have discussions later, but that's the overview of mixtures.
Question for Randy before we bring Brett up here. I just have a quick question. So if we want to combine the factor with the mixture, can that happen too? In one experiment? Yeah.
Well, that's the mixture amount. Is that what you're talking about? Yeah. Right, you'll have the mixture aspect of the experiment, and then you can add in the non-mixture, okay? And you can add, now I just showed one factor added, amount. You can add others, okay? And we could play with the geometries, okay? And that's kind of cool. But yes, you can mix and match to match exactly what you need.
Thank you. If anyone have more questions, we can meet Randy at the end of the talk. So Brett, we will welcome you up here. Thank you.
Hello, thank you, welcome. So first of all, I wanted to include R code in here, and it's really small, so if it's not too inconvenient and you want to see things, you might want to get a little closer. But you guys can make that decision when you see how small I put stuff in there. Anyway, my name is Brett. I work at Tissue Grown Corporation. We're a commercial micropropagation company. We've been making like millions of pistachios a year for a long time. I primarily do research there, so I use R regularly for doing experimental design, trying to optimize these micropropagation systems. Fortunately, I have someone to make media for me, and people to label the media, and people to cut the plants. So I pretty much just organize the design, give people instructions, get plants to put on there, and then I can analyze the data later. So I'm in a very fortunate situation because I can do a lot of these designed experiments because of the support team I have in place. So how many people here use R? Okay, we got some R users. Anybody using R for DOE? Okay, Micah in the back, that's my guy. So I personally was using Staties for a really long time, and I think it's fantastic, and if you're just getting introduced to DOE, it's a much better way of doing it than trying to figure out R and DOE at the same time. It's just a lot to learn. But so for me, what happened is Staties, the commercial license costs about $1,000. And so I had a computer that had 2 gigs of RAM, and I wanted to change that. And I did that, and I realized my Staties license had expired. And so instead of spending a lot of money to get the commercial software, I just started using R for my analysis. And I haven't looked back. I think that if you do take the time to learn it, it'll be a superior medium for performing DOE because it allows you more flexibility. But again, it's harder to use. So forward. Okay, so starting the presentation. Why R? And what is R? So R is an open source programming language that's developed by statisticians. The cool thing about it being open sourced is a lot of people who are way better at statistics than me develop these packages, and all you basically have to do is read their paper about how to use the package, download and install the package, and then call the functions that they have created to do your analysis for you. This, in addition to being really good for design of experiment, R is fantastic for data manipulation, data visualization, simulation. One great thing is it's a scripting language. So if you write instructions to a computer, you can take a more extensive data set and you can plug it in and those same analysis will work. It's free. Like, that's a really good thing about any, especially when you're taking the time to invest to learn software. If it's free, it gives you a chance to try it out and see if it has utility to you. If you do learn R, you will be better at your job. I promise you, you'll be more hireable. The things that were taking you a long time before, you'll do almost instantly. I'd highly, highly recommend learning at least one programming language for your day-to-day work. And if you're interested in DOE, it should definitely be R. Anytime people talk about R for data analysis, people are going to bring up Python also. It's another one of the programming languages that people can use for doing data analysis. Python's really cool in a lot of ways that R isn't. But if we're specifically looking at DOE, it's much better to use R because there's a lot more literature out there. So I was flying in, and I've been personally learning Python for controlling microcontrollers. But I wanted to read some Python and some DOE on the plane in. So I was looking on Amazon, and there's not a single book. So to me, that's a big problem because the literature base isn't there teaching you how to use the software for this particular application. And while R has a whole bunch of great authors and really fantastic literature out there that's specifically aimed at statisticians. So R can do a lot of other really cool things. So part of a job as a researcher isn't just doing the research and collecting the data and analyzing it. You have to present it to the decision makers in your company. So R has and it's through RStudio, but they have a tool called R Markdown where you can basically generate these dynamic reports, and then you can update your data and run the same report. And so you can basically combine text and code and data analytics in a format where decision makers can easily understand what steps you took in your analysis, and you can use normal person talk to try to explain it. There's a package called Bookdown or Blogdown that you can use to make websites. You can write books. There's a package called Shiny, which lets you make these interactive applications that, just like web apps, you can use for presenting like key production or KPIs or anything people are interested in. You can make interactive apps. And beyond those things, it's really great for simulation. You can do more advanced statistical analyses, such as like Bayesian modeling. I'll talk about it a bit in my presentation here, but I struggle a lot with the assumptions you're supposed to make with the standard frequentist statistics approach. And if you can convert things into like a Bayesian format, basically you can define what all of these distributions that you're pulling from are, so your probability values are more representative of what you intend them to be. So R is not that easy to learn. It's definitely going to take a good amount of time. If you already know it, it's pretty easy to convert your understanding into design of experiment. This book by Hadley Wickham is free, and it's an amazing book that's going to teach you primarily about something called the tidyverse packages, which are so when R was first made, it was made with, like, you call it base R now. There's different dialects of R, and so in base R, it's very difficult for people to learn. It's amazing, but it's less accessible. And so this group at RStudio, Hadley Wickham especially, came up with a bunch of these packages called the tidyverse, which are supposed to make your job as an analyst work easier. So I would highly recommend, if you're going to take the time to learn R, you do focus on the tidyverse dialect and the packages contained within. Another way I learned was using this web application called DataCamp. It's kind of nice when you're starting out that it just provides things in a really simple step-by-step way for you to learn. So I personally believe that all you need to really learn R is to get good enough that you can use it at work and be more efficient than what you were doing before. And so without too much work going into it, you should be able to reach that point. And then realistically, till you're not having to ask questions on Stack Overflow all the time, it'll be probably a couple of years using it. But once again, too, the thing at the bottom, like if you have questions, if you can figure out the right thing to Google it, go to Stack Overflow, someone's going to have already come up with a solution, and then you can just implement it in your specific application. So to install R, you can just go to CRAN, install the latest R version. You'll need to pick out an editor. If you're just getting started, I would recommend using RStudio. It has this interface here, and yeah, here's where you guys might really want to consider getting closer if you want to see things. But so RStudio is a great editor. Up at the top left quadrant, it has where you write the code. So the area, the bottom left quadrant is called the console, and so you'll write the code and you'll execute it down in the console. And so it shows plots up on the right. Up at the top right, that's your environment. It shows all the variables that exist. I personally don't use RStudio anymore. I used it when I started out, but I was spending probably 4 to 6 hours a day on R. And so I upgraded my editor to an editor that you don't have to use. You can use only the keyboard. It's called Emacs. If you spend a lot of time coding, like I would highly recommend being able to teach yourself how to not use your mouse, because you just end up wasting so much time like point, click, drag, when you can just be like, I'm data analyzing. So, okay, some basics on R. So up in the way I have it set up is the code is on the left, and the code execution is on that section on the right. So how many of you guys can see this right now? Okay. We probably, this is just some basics on R. I wanted to, these presentations are supposed to be available, so if anybody's really interested in learning R, maybe you guys can just go back and look at this later. This is just some basic overview of how to use R. It's talking about the basic data structures. You have to understand there's a difference between numbers, factors, booleans, which are true and false, strings, and I basically funneled things down to having a data frame at the end, which is the primary form of data that you're going to use in R for analysis. A data frame is basically just like a Microsoft Excel spreadsheet that has your column names and data in all of the columns. So it's a two-dimensional thing of data, so it has to have the same dimensions also. So you can't have something with like 100 columns or 100 rows in one column attached to something that only has 5. So the structure has to be like a square. So if you're going to use R for DOE, unless you are extremely, extremely good at experimental design and want to waste a lot of time making all this stuff yourself, you'll want to start using third-party packages. As I mentioned earlier, there's this tidyverse package, which has a lot of really valuable tools for data manipulation and visualization. The two that you'll probably need to use the most are one's called ggplot, and so that's a basic plotting package. It's fantastic for visualizing data. If you have a data set, you can look at probably 10 times as many graphs in the same amount of time as you would doing it with Excel. And there's a lot of tricks you can do to add dimensionality to the way that you're looking at data, because you're not really going to get that much out of it from just doing regression analyses or just like looking through and trying to find where the higher numbers are. You really need to get competent at visualizing your data to have a good relationship with it. There's another package down there called dplyr. It's supposed to be short for dataplier, but that's basically how you're going to take your data and just hack and slash it into the form you want it to be in. But more specifically, there are amazing, amazing DOE packages. Some of the ones I like to use are that FR-F2 package by, I'll probably say the name wrong, but Ulrich Dromping. So that's for factorial designs. They have everything in place to build the factorial design, and then the normal plots you'll use for analysis, like a half normal plot or your main effect plots, your interaction plots. It talks about all the aliasing in the design. Basically, there's like a paper you can read on it that if you read it, you'll be able to, and you know R, you'll be immediately able to implement that package to do your factorial designs. There's a great package for response surface methodology called RSM. We're particularly looking at mixture experiments, and so I use a package called EXP by John Lawson. And he also published, he has a fantastic book. It's just Design of Experiment with R. And he talks not just about this package, but how to use R in general for design of experiment. If anybody is interested in this subject, like I'd highly recommend reading it. It's dense, but you'll get a lot out of it. But there's an exhaustive list on this website CRAN that's just everything R. So you can go to that link and find all these packages that people have made. It's a wealth of riches. So install a package, you basically want to just go into your R interface. Once it's installed, type in install.packages, quote, package name, and then in the future, you can just call that library. So you just library package name. Sometimes it's a little difficult to install the packages. They'll have like dependencies that you'll have to install somewhere else. But realistically, it's just the price you have to pay to being able to use this amazing tool. Anytime you have trouble installing something, there's always help online. One other challenge I had when I was first getting started with R is trying to navigate the file system without a point-and-click interface. I don't know how many of you guys have used the terminal to access your file directory. When you start using it and you just type in your file name and hit tab and your editor will pull up a bunch of options of the other files in there. It's really easy and it's really fast, but it's also very weird. I mean, it's like a Macintosh world that we want the prettiest, nicest interface. But if you're going to be doing something with a text-based way of doing it, you realistically need to be able to navigate your computer to know to export and import files in the location you want to find them. So you can basically read data of any sort in with R with the appropriate function. The example I have right there is just for reading a CSV file in. So basically, you just call your function, and the functions are, if you see me put parentheses in there, in R, you're calling a function. You're going to do that. R is a functional programming language, so you're going to, like a lot of programming languages, you basically build the tools you need yourself and then use them. R, you kind of just go find the tools you need and use them. So you hear me say function, sorry, I got to try to avoid the jargon, but you can read CSV files in, Excel files, whatever format you want to use, and then you can save them too. And so you have to be able to design your experiment, save it in a secure location, do your analysis, record your results somewhere, and then import that for analysis. So it's really important that you get used to navigating the file system in R. If you're going through and you just hit tab, usually it will give you all the options. It's pretty straightforward once you get used to it, but it's a little weird. So in R, you're going to need to learn to use the package called dplyr, or you can do it with base R. It's just really easy with dplyr to do the basic operations you're going to need. There's only a few functions you need to use. One of them is called mutate, and that basically takes your data frame, your two-dimensional data frame, and it adds a column in with whatever mathematical relationship you want. The filter function's one you're going to use a lot, and so it will take a row. You define basically the column. Like in my example, I say the column is plant. If the plant is equal to Arabidopsis, leave that in the data set. And then that will basically just let you focus on the data that's of interest to you. All of this stuff is in that book, R for Data Science by Hadley Wickham. If you're just read it. If you're interested in learning R, it's free. It's easily accessible. It's much less dense than the DOE books, and it will really get you up to speed understanding how these basic data manipulation processes work. A couple of the other ones are you have to be able to group your data and aggregate it. So a lot of times, if I have an experiment that has, say, I have 16 runs with 5 samples on each of them. If I'm communicating my results to someone who's not as interested in the in-sample variation, it would probably behoove me to take those things and just reduce it down to 16 runs. And so that little group by, and then there's the little parentheses with the greater sign, which is called a pipe. It's another weird R syntax thing. So you can use that group by and summarize to aggregate the data based off any mathematical relationship you want. And so that's going to be a really helpful tool. And then the last one that you really need to know is how to join data sets together. So that operation left join, basically you can say in this data frame, I want this column to equal this column and this data frame, and it'll just put them together into one bigger data frame. So getting into plotting, it's much more important for me to visualize the data than to look at statistical summaries or just looking at things like a compelling data visualization is so much more valuable than just having data. So the package ggplot has a bunch of really fantastic graphing tools. You have to have clean data going in. So basically, if you're doing it, your data has to have a certain structure where each row. So you have all your columns lined up, but then each row needs to be a unique addition of each one of those observations. So if you can learn how to use ggplot, you'll be able to take your data frame and visualize data with a lot of added dimensionality. I use it throughout this presentation, so I can show you guys some more later. So I wanted to talk about, there's a very famous data set. It's called Anscombe's Quartet. And the reason it's popular is because it shows you the value of data visualization over using statistical summaries. So the code's kind of hard to read and probably isn't that important, but you can see the plots on the right. It's all very different data, but the regression summaries for a linear model, not for, if I'm not including a quadratic term, but in a linear model, they're exactly the same. So you can see the little blue line has the same slope, and furthermore, in there, the R-square value is the same. So these four very different presentations of data have an identical statistical summary, but if you visualize it in basically like 2 seconds, you can see, whoa, that's really different. So you can see the form of the data in the top left. Now, in order to plot that with using the ggplot package, you need to do a little bit of data manipulation. So they have, the row names or the column names are x1, 2, 3, 4, and then y1, y2, y3, y4. So you have like a 8 by 11 data set. Now, in order to use that in ggplot, I basically wanted to combine that into the 4 groups. So there's x1, y1, x2, y2, x3, y3, so on. So I needed to basically, I say the first line of code, it says group 1 is the Anscombe data set. I'm selecting column x is equal to x1, y is equal to column y2, and then I use the mutate command to basically just create a new column called group, and I'm just going to name this 1. So I do this for the four variables that are in that data set, and I use the rbind command to basically just attach them in a vertical orientation. ggplot can be a little picky based off your data structure. So the first time I made the plot, it worked fine, but stuff wasn't ordered. And so to me, I thought it's a better presentation if you have the group names 1, 2, 3, 4 organized in a not random matter. So you have to change the data structure so R knows like the order of the levels. And then you get into the structure on how you would call a ggplot. And so basically, you just define your ggplot with the ggplot function, and then you define the geometry you want. Now, in this case, I'm using the point geometry because I want a dot plot. And so I just put geom point. And then I also wanted to have a regression line in there, so I put geom smooth with the argument method equals lm, and that gives me the line. And then you can do something called faceting, which basically, instead of having one plot that would have all of those data points on there and it would just look like a mess, you can split those into the 4 groups and look at it at one time. So this is a really nice example of where you can basically look at 3 dimensions of data in a very short period of time and get value out of it. So if I were going to look at this in one plot, it's just a mess. Like there's not anything I can get out of it. But as soon as you pull out the relationship on the groups, you can see your group relationship, your x and your y. So you're looking at 3 dimensions, and being able to visualize more dimensions, which is possible in more ways than this with ggplot, it's tremendously useful. So R has its own base plotting function, and so I basically do the same analysis here. Now, these plots call for different structures. So for R's base graphics function, you're basically just going to provide 2 vectors, which are like one-dimensional sets of data, like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And so you just say X and Y are your vectors of data, and then you define what the plot terms are, like the limits. So this is what the code would look like to basically produce that exact same data, but with base R's plotting function. I personally use ggplot a lot more, but there's a lot of really cool things you can do with base R. You can iterate with plotting really well with base R. So say if you take a statistical simulation, you can sample basically random error terms or your response estimates, and you could basically just plot like 100 lines in a super small period of time, so you could see what things look like in terms of error a lot better. But I would personally, if you're just getting into it, just learn how to use ggplot. It's way easier. It's super versatile. So I wanted to talk about this whole section in order to explain why regression can be dangerous without visualization. So if you look at the top right call, which is going to be really hard to see, but it has it basically is a regression summary. And so if you're just getting started, all you really need to know probably are the coefficient estimates and your probability values. And then obviously the R-square is super important. I like particularly they have an adjusted R-square in the normal regression summary in R. Overfitting is like a very large problem with data modeling. So if I have any group of points, so I can basically get a perfect explanation of the variation if I use enough polynomials. So it's nice to see an adjusted R-square in the regression summary because it penalizes your model if you include more factors. So that way you're not like, if I add factors to the model, I can eventually always describe the data perfectly just because there's more explanatory variables. But so in there you can see your R-square, that's the important thing, your adjusted R-square. You'll see, so the top one and the middle one, I did X1 and X2, which going back to group 1 and group 2, you can see there's a very clear quadratic relationship on group 2 and not on 1. But so if you don't include the quadratic term like we're doing with this line plot, you'll see the regression model is exactly the same. The R-square is the same, the coefficients are the same. You're definitely, if you don't visualize it, going to lose some potentially really valuable data. So you can see at the bottom one, I included a quadratic term, and it basically perfectly explains the variation as it should because someone just randomly selected a quadratic relationship for that data. Okay, so I wanted to start off with doing a completely randomized design with one factor. This is the tools you'll use in this are going to scale very well to a lot of other analyses. It's basically the exact same thing as response surface methodology. It's just you're only looking at one dimension. It's a little, like the analysis is a little bit different than you're going to do with factorial designs just because your data is, like we wanted to use analysis of variance instead of regression. But you're even if you do them wrong, you're still going to get pretty good results. It doesn't matter that much. So what I did here is I took it's a real experiment I've run. I have hypothetical data here. I just randomized it, so don't copy this data and say my stuff didn't work. But so this experiment, we're going to hypothetically just try to optimize the effect of IBA on rooting. Super simple. Anybody who's done tissue culture knows that the IBA level, if you're doing an induction expression system where you put the plants on a root induction media and you take them off, is going to almost certainly have an effect. Like the auxin makes roots, so why not look at what the concentration of auxin does? So in this, I want to cover the steps of basically how to set up our environment, how to create and randomize a design, how to export our design for later use. Is that me? No. Okay, that's good. Determine what the experiment size you should do, visualize your data, fit some models to your data, check your model's assumption with diagnostic plots, and then confirm the results in a follow-up experiment. I personally believe that confirming your results in a follow-up experiment is the most important part. Any of the decision makers I'm used to, they just want to see if it works. They don't care about all the statistical analysis. They don't care how clean my R-square value is. They just want to know if it works, so they just want to see one compared to the other. So here's some basic R code of how to set up this design. So I basically, the little colon things are comments. It's parts of the code that won't be executed. And so I'm installing the packages I want to use. So I want to use the tidyverse package, and I want to use the DAWR package. I'm setting a randomization seed in the next line of code. So if I come back, it'll have the same randomization and generate the same design. So I use that setwd command to set the working directory. And then from there, I go into actually making the design. So I need to, at this point, make a vector of data which has my IBA levels. So I'm taking that sequence function, and I'm going to make a sequence, SEQ, from 1 to 7 with 7 inputs, which is the length out part. And so you can see it's randomized on the right, but it gives us that list of IBA levels, 1, 2.5, 4. And so I want to take that, and I basically want to randomize it. So I use and I need to also convert this into the data structure called the data frame, so I can use plotting packages. So I basically just make a data frame by saying I'm going to have run number 1 to however long my IBA vector is, and then the IBA level, which is I'm using the sample command, which just takes that vector and randomly pulls out one of the numbers. And if you put the replace argument at false, it won't replace it. So if I put design without having like an assignment operator on there, it prints it out. So that's what we're seeing on the right. And then I'd highly recommend that you export your design somewhere separately. I mean, you can comment out the code or delete it. You just want to have your actual design like put in a different area where you can't mess it up. At one point in R, like I updated my R version and they changed how the random number generator worked. So everything that I didn't have set aside, I basically like lost all of that data, and it was pretty catastrophic. I had to do a lot of work. So there's a lot of really fantastic tools for power analysis. So I'm using in particular this DAWR package for power analysis. And this particular function has a lot of assumptions about normality and other statistical jargon, but it basically allows you to tell me define what your confidence interval is, define what your standard, your variance is expected to be, sigma is the standard deviation, and then you tell it basically how large of a difference you wanted to detect, and then how many levels, and it'll give you this nice printout that basically shows me that if I do this experiment with 7 levels, I'll need basically 27 replicates in order to achieve a 97% probability of detecting a 20% difference if my standard deviation is 15%. So personally, I don't really use these that much. Tissue culture is really easy to do research, and I would just err on the side of having more replicates that I need. I also get very confused about assumptions. So in this particular example, I'm looking at rooting rate of plants in a magenta box. So I have a box of 9 plants, and whether it roots is not, that's clearly a binomial, is binomially distributed. It's yes or no, does it root? And then there's a probability value inherent. And so if I'm entering my data and I'm measuring it by box, I'm saying 5 of 9 rooted. So I think it's pretty safe to assume at this point my data is not normal, but for these probability estimates to actually be accurate, I have to have all of these assumptions satisfied, and I'm skipping out on them being logical. So I personally don't take a lot of stock in the actual numbers that the power analyses or any probability values tell me. This isn't the best practice, I'm sure, but if you can tell very easily if your model's fitting the data well, but I wouldn't go up to a decision maker and say I have a 97% chance of this being right because I probably messed up on the assumptions. So going through and visualizing the data, so importing some data and visualizing it, I left some points that are below 0% rooting in there, so you guys know it's fake data. So yeah, once again, fake data. So the first line of code there, I say results is basically assigned to, I read in a CSV type file, which are fake results, crd.csv. Then I'm going to basically import the design from where I saved it earlier, just so I know I'm working with the same thing. And I use that left join function to basically join things by the run column. So from there, I can then visualize the data, and the code right there provides that nice data visualization where you kind of assume it probably has a quadratic relationship, and in which case your one-factor optimization was successful because you should be able to estimate what the optimal level is in this case. So going on to fitting the models. So that LM function that you see up, so it's like LM function data is equal to design import. So the first model I do a regression summary of here, I don't include a quadratic factor. It's just it's just a line, just a regression line. The second one I do include the quadratic term. So it's really interesting because in the first regression summary, if you look at the multiple R square, it's 0. So if you were just going to go through and not visualize your data, you would learn absolutely nothing from this experiment. You would think it's a complete failure. Like, it looks like really bad statistics there. But when you include the quadratic term, which you can somewhat see from just visualizing your data, you can see that this model actually, the R squared for like the adjusted R squared is about 35%. So including that quadratic term goes from my model having explained basically none of the variation that we see to explaining about 35% of the variation. So that's not like, people are like, oh, 35%, that's not that much, but it really, I mean, that's a big chunk of the variability to get taken out of it by adding one factor. So it's really important to note that if you had aggregated the data, so this plot here shows what the data looks like aggregated. So you can see that the points are a lot closer to the trend line here. And so had I aggregated the data before I ran my regression statistics, I would get much cleaner looking statistics. So, if people are, if you have to have some sort of amount of the variation explained, like you can aggregate your data, it just basically pulls out the in-sample variation, and it spreads that out over the 7 factors instead of each one of the individual levels. But anyway, so R has a really easy way of looking at your diagnostic plots. So you can just take one of those regression models, and you can do that summary function to get that nice printout that shows you all the stats. Or you can just plot the regression model, and it gives you these diagnostic plots. I don't know how many people are familiar with these, but 2 of the ones I look at a lot are the QQ plot, the quantile plot, which basically checks to see if your data is normally distributed. Instead of getting like a line, you'll end up getting like an S-shaped figure oftentimes when you're not getting normality. And so then you kind of need to go back and check your assumptions or do like a data transformation. Another one of the ones that's important is the residuals versus fitted plot. It basically checks for non-constant variance. Another one of the assumptions doing experimental design is constant variance. So if you end up, instead of having like a random field of numbers like we have there, it's the top left of the plot, you would end up getting like a cone or some sort of, a reverse cone. So at the end, basically, I just got my prediction function. So this mathematical function now predicts what the relationship is between IBA and the rooting rate. And so then I can figure out what the max level of my prediction is. And you'll see here that based off this function, I probably should put about 5.25 milligrams per liter of IBA in my media to get the highest rooting rates. Once again, that's the code for how to visualize that. And you can see the group by and summarize functions I used. That's how I aggregated the data to basically pull out. So it's only one plot per level on the x-axis, or sorry, 1 point per level on the x-axis. So moving on to response surface designs, they're very similar to the one factor thing I showed you here. It's just more factors. So I'm using the RSM package to create this design. And so I call the function CCD for a closed central composite design. So I don't know how many of you are familiar with this, but a central composite design is basically just like a circle inscribed around a square with some center points. A lot of people will look at it as like a cross with a square. So to define the central composite design, I basically just need to tell it how many factors I want in the design. I'm saying I only want one block, with that one block equals true. The alpha equals rotatable tells me how far out basically the star points are, which are the ones that basically make the circle thing that goes around the square. And then n0 is how many center points. And then the coding is basically defining what the names of my factors are going to be and the levels. So I can put this function in there, and it'll spit out this design. And so this is a design, this is an experiment. I love this experiment. If you're doing tissue culture and you're having trouble rooting stuff, I would highly, highly recommend this. So I'm taking, it's just an experiment set up to optimize the IBA level, the sucrose level, and how long it would sit on an induction media. I've had a lot of success with this experiment in the past. So I'd highly recommend that anybody explore the sugar level, the oxen level, and then how long it sits on the media. You can throw temperature in there. You can make these designs as complicated as possible, but they expand very rapidly in the number of runs you need. So it's really easy to bury yourself in work if you want to try testing too many factors at once. So I'm not going to go and analyze any data here. I'm just showing about the setting up the design. So I was talking earlier about how in R you can, and using ggplot, you can add more dimensionality to your visualization. So in this case, we have a two-dimensional visualization, which is your IBA and your sucrose. So that's your X and your Y. And it would normally have a nice square with a circle transcribed around it, but I added a little bit of variation so the points don't overlap perfectly. And then I made it so the color is basically the time. So you see the lighter points in there are there for a longer period of time, and then the darker points are there for a lesser period of time. So at this point, we can actually look at three variables in this one plot, and that's just a very useful tool to have. So setting up fractional factorial designs. Again, there's another package that has tools in place that if you read it's like a 20-page paper someone will write, you can implement these tools to set up and analyze your design. So the design is set up with that FR-F2 function. So you basically say how many runs you want, how many factors you want to include in the design, and then define what the factor names are and the levels. And then if you just do a summary of the design, it's going to give you this nice printout that shows you basically what your design levels are. It shows you what factors are confounded. Confounding is a really big problem with factorial designs. The benefits you get from being able to use less runs compared to a full 2 to the whatever number. In this case, it'd be 2 to the 5th. So we're only doing a half fraction. But if you have they have that resolution chart, and if you've done experimental design with, I'm sure you've seen this, which tells you whether it's the resolution of the design. And so in this case, I have a resolution 5 design, meaning that your two-factor interactions are only going to be aliased with 3-factor interactions. And so 3-factor interactions are generally very rare, so you can kind of assume it's not going to happen. But if you get into your resolution 4 designs, you get 2-factor interactions that are aliased with other 2-factor interactions. And so in a system with a lot of variables, it's unlikely a specific interaction exists, but it's very likely an interaction exists in your system. And so a lot of times you'll have to do things like folding the design or adding, doing follow-up work, which this FRF2 package has all the tools in place to do this. But it's just a word of warning before being you want to do a screening design that has the minimum number of factors. It's really very easy to miss important interactions. So in factorial designs, one great tool is the half normal plot. So the half normal plot basically just plots the absolute value of your effect estimate. And so you end up getting a bunch of, the factors that are important end up basically deviating from what would be a straight regression line from the other data points that aren't labeled there. And so you can call this super easily with this function just called Daniel plot. You just put in, as long as you attach your response, and you have to use that add response function because the structure of that design is not actually a data frame. It's a specific structure of something meant for analysis with this package. And so you have to use the function already built in to attach a response to it. But so if you attach just a response vector, which is just a line of numbers, to your data, then you can use the plotting functions that are already built into this package. So calling Daniel plot just immediately gives me one of those half normal plots. I can see that the sugar most likely has an effect. I can't actually see if it's a good effect or a bad effect from that picture because it's only an absolute value of it. People will often look at just a normal plot, which has, like the positive effects on one side and the negative effects on the other side. So it tells me that the sugar in this use is probably important. The fungicide that I have included in there is probably important, and then same with an interaction between the sugar and the environment. So that ME plot function gives that plot below. Super easy, just type in ME plot and your design with the response on it, and it prints out that really nice visualization. The interaction plot does the same thing. I use the select function there to just focus on the sugar and the environment. Otherwise, you're just going to get, in this case, a 5x5 matrix with a whole bunch of plots that's kind of unnecessary. So in this last part too, I have a summary of the analysis of variance. Here I'm using the AOV function instead of the LM function just to specify that the data that I'm using, it's not numbers, they're factors. So you should use different tools. Realistically, the probability values are almost always the same. So I was doing it for years with the wrong thing, and it seemed to work just fine. It's mixture designs. Here's the fun stuff, right? So Dr. Neitz earlier was talking about these triangular coordinate systems. So these plots here are a way of looking at a mixture with 3 components and a process variable. So I'll go back, obviously, but they have, in these 2 plots, I have 3 different salt mixes that I used, and I combined them, and then I did the entire operation at half strength and then 1.5 strength for the salts. And then so you can see basically what your model predictions would be at these 2 process levels. And so those little triangular slices are pretty much exactly what we saw in Dr. Neatz's presentation earlier. You can extend these as much as you want. I mean, all this stuff is infinitely extensible. So setting up the model, you go through the same process where you set up your environment and you make sure your packages you're going to use are installed. You make sure to clarify that you're going to use the same randomization through all of it. Make sure that you're in the right file folder. And then so you can move on to setting up your design. And so here I set this design up with 3 random salt mixes. I don't actually know if there's a good way without doing a tremendous amount of work to do salt optimization where you don't have a large degree of confounding. Part of me hates doing an analysis that I just take 3 salt mixes and mix them up because you don't know what's causing what. And as a scientist, a cause and effect relationship to me is very important. You kind of end up with more like a black box. You're like, well, this area, the plants grow well, and I guess that's okay because it's repeatable. But you don't understand why if you're doing it like this. But on the flip side, it's really easy to make the media. If you want to go through and if you want, if I were to take all the macros, if I'm going to take all the cations, all the anions, and I want to do those in a term where I can get, even with just doing a process design where I have 2 levels, you're looking at it like a 256 run experiment to do 2 mixtures and a process variable, and that's just not realistic. It's gonna go bad if you try to go into your media prep person or do it yourself and make 256 runs. It's just not gonna go well. So you got to try to figure out ways to keep things small while still answering your question, and then so to me it's nice because if I take 3 media and I just mix them up in different amounts, it's really easy to do the media prep. So in the code here, we're at the grand finale right here. Got to mixture designs and the fireworks went off. So the particular, the meat and potatoes of this analysis is that, or the setup, is that xvert function and the fillv function. I think xvert is the name of the algorithm that is the space filling algorithm people use for experimental designs or for mixture designs. But anyway, so if you look at this particular triangle with 3 levels, and if I do that xvert function with the number of factors being my mixture components, which is just my 3 factors with the lower bounds and the upper bounds that I have established, it'll end up giving me 4 points. It'll give me a pure blend at x1, x2, and x3, and then a center point that's a 1/3 mix of all three of the salt mixes. So then, because I wanted to add a little bit, there's still a lot of, like, experimental design is very much about dimensionality, and you can see how much space is not occupied by my design if I only have the 3 vertices in the center point. And so I use that fill v function to add basically like that circle of points that's like the half and half blends, and then the 2/3, 1/3 blends. So when that's established, I'm basically using that rbind function we looked at earlier when we were talking about that Anscombe data, and I can take all the points in that plot there and just slap them on to another level. So process level A, process level B, slap them together, and you have a mixture process design. From there, I still need to randomize it. You always gotta, it's always a good idea. It's so easy to do to randomize it. So I use that sample n function to sample the points that I've established, and then I just save the design as a CSV file, and you can see I printed out just the head of it there. I didn't want to go through all. I think we're at 20 runs here, and so you can see like run number 1 is going to be 50% salt mix 1, 0% salt mix 2, 50% salt mix 3, and 0.7 times the salt strength. I actually did 0.5. That's a mistake. But you can see they have the low level for salt strength and the high level, so that's my process factor, and then the blends that you can see in that triangle. So getting into some results. So probably the hardest part about doing data collection is figuring out like how to score things. It's really important to run these analyses for multiple passes, and so you can't just go through on the first pass and say, hey, what's your dry weight of the plants? So I just go through and I score them on a scale of 1 to 5. Like the box on the top looks pretty good. The stuff on the bottom looks like I'm not making any money. So they're random. So I just score them, record the results, and then you can see basically I just have a plot that's all we're looking at here is the effect of the process variable, the salt strength. And so you can see for the 2 lines that I was working on, like Hanako-chan and then Uch, 2 different peony types. In both cases, the higher level of the salt mixture was a lot more, it was a lot better in terms of my perceived quality than the lower mix. And so you can we can go into our mixture tools at this point, and you'll see that the one on the top, the little red and yellow plot thing at the top, that's salt strength 1.5. It has higher numbers than the one on the bottom, or maybe you can't see. But the best results were basically a media that was pure salt mix 3. That's at 1.5 strength in this experiment. So to get there, though, you basically need to take your results and you need to feed them into a tool that's in the mixture experiment, the mixture experiment package. And so you'll get a regression model from doing the code that's right there, like that mix model function. I put the results in. I say I want to model the quality. And I define the mixture components as salt mix 1, 2, and 3, and then the process variables as the salt strength. And then you have to define the type of model that you want to use. In this case, it goes on a scale of 1 to 6. If you're doing like a mixture amount design that has more than 2 levels on your process variable, you could put that at 6 and it'll give you a different regression model. So then you use basically this model plot function and it'll give you these really nice visualizations. It's kind of gross looking at it. Like I wouldn't be able to write this from scratch. Like I'm just going to look it up or copy and paste from a previous analysis and then just change the arguments. So, these plots, you can do a lot of customization in them, and you kind of don't need to know how all that works. You should just go read John Lawson's paper, the person who wrote this package, and then basically just copy and paste from his thing and change it to your design. But so, we end up getting a nice visualization that shows us that at higher salt mixes, we got generally better quality. You can extend this in the case that if we had, if I wanted to have salt strength at 10 different levels, I could easily have 10 plots here to visualize it. The data visualization with R is extremely flexible. So that's pretty much it. There's really no limit to what you can do with R. R grows as fast as like research in the statistical community does. There's a lot of professors who are, they come up with new methods and they publish them and they put R packages out to help you with these analyses. So there's any kind of design you can think of. If you want to do optimal designs, like if you're in a system where, for me, experimentation is really cheap because we're just cutting plants. But like if we were doing a system that I had to, like build a plane and see how like the shape of the plane wing works, it's not realistic to have like 100 replicates. So you might want to use optimal experimental designs. That's like a whole nother field. DOE is very dense, but all of these tools exist in R and so much more. So thank you guys so much for the opportunity. I really appreciate you guys being here and letting me talk. If you have any questions on R or DOE, reach out to me. I'm happy to help and to get you started. One thing I do want to stress is, so like I don't think you need to be perfect at this to get a tremendous amount of utility from it. I'm self-taught. I don't have a PhD. Like I like to read. And so when I started doing DOE, I didn't know nearly as much as I know about it now, and I'm still learning. But I still got good results, much better than I would have without having some sort of framework for explaining things. And I believe that any bit of investment you make in learning DOE and learning R will pay out, unless you're like 3 days from retirement and never want to think about it again. Like it's worth doing. Every day your work is going to get easier if honestly it gets harder because people ask you harder questions, but like the things you used to do without using R become trivially easy, and then you're able to then move on to doing more complicated stuff or stuff that's more specifically suited to your application. Thank you so much. I appreciate you.
And thank you everyone who's still staying here despite of we have beautiful fireworks, I guess, out there. So thanks again for still staying. So do anyone have any question for Brett or Randy that we can happily answer today?
Yes.
We have. Okay.
We got one.
Got one, finally.
I fit in your latter class. I'm retired. I have no desire to learn R.
Wait, I'm coming closer. I can't.
I am retired, and I have no desire to learn R. However, we give a workshop in R for the use of genomic data for developing countries. What we have is a canned program using DartSeq, a particular, and it also applies to SNPs, particular genetic markers, that we give them, that they can walk away and use those programs without our assistance just by downloading RStudio. Where are we from getting such a canned program that we can take our scripts that already exist and use them for DOE experiments for defining tissue culture variables?
Okay,
Randy, I talked to you about this earlier.
It actually exists.
Excellent.
One of the big R packages people use for genomics data is Bioconductor. And so if you're using R and you're doing genomics data, you're gonna like get buried in this package. I personally don't work with genomics data, so I don't have that much experience with it, but I've heard about it a lot of times. There is a specific like point and click interface that's based on R for doing data analysis. I tried to use it when I started using R, and it just, to me, it was not so much of an investment that it wasn't worth just learning how to do things line by line. To me, it was harder to learn that piece of, like learning Staties. It's not trivial. Like the first time you open up that application, you're gonna go cross-eyed looking at all the options you have. And so because there's that same wealth of riches in the data analysis package that R puts out that uses R, it's free. You just download it and install the package, and you can have a point-and-click interface for doing analyses. I don't remember particularly if they have a lot of stuff with DOE designs with R. I mean, honestly, like it's something you could write. Like I could write that in a couple, like a week or two if people have interest in something like that. I would advocate though, like it's really, R is, it's going to take over your life. Like every single job you do, you're just going to be like, well, I can do that in R like really quickly. And so once you learn to just, you know, if you want to say, like you just type, for example, like some of those functions, I just say MEplot, and I say the data I want to use, and it pulls it up. So I'm using like an editor Emacs where I don't have to take my hand off the keyboard. I can type pretty fast at this point. For me to just go MEplot, looking at my data, okay, IAplot, look at those factors. It's so much faster, and it's so much more of an intimate relationship with your data that I think that it's like you're not going to want to touch your mouse. You're just going to want to really just bury yourself in the data and be able to ask questions of your data. And you can ask questions of your data almost as fast as you can type, which is kind of staggering because that's just not, you know, if you're in Excel and you're copying and pasting columns, it's really tedious. So these things exist to some level. I can try to get your information later, and I can look up what that package was that has the graphical user interface that runs on R. But yeah, I mean, specifically for DOE, I don't think it's that hard to just learn a couple of the functions. As long as you understand the design of experiment framework, the R should be pretty straightforward.
That's what I'm asking, is for a simple, canned type thing. This is what we present for genetic data. Why can't we get those simple functions in R? I don't want to learn R. I have no desire to. Why can't we get those simple functions in line with defined filters so that we can use R as a tool in our analysis of tissue culture medium? Is it that hard to do? I mean, the formulas are out there.
It's really easy.
Exactly.
Like
so,
if there's interest, I'll do it. You know, if people are interested, I'll do it.
So maybe that's the next. Maybe that's the next generation.
Share the love.
You come to me or to him?
So you mentioned on one of your graphs, you had pretty much copied out the code to generate the graph from that guy's book.
Exactly.
And then you just tweaked the parameters.
Yes.
I think what he's asking is, imagine, because there's some standard designs that probably people could use right away. And so let's say it's a mixture amount, 3-component, okay, amount. So you just have the code, just like you have there, and then there's like little notations. Okay, if you want this, change this number here. And then you just copy and paste right into RStudio and run it.
So
I think that's kind of what he's getting at. Right,
Well, so there's that R package Shiny I discussed that lets you basically build interactive web applications. You could use that package, and you could write I could write what we're talking about here in 6 hours. If people have interest in using it, it's really easy to set up. It's really easy to post it for free online. Like, if people are interested in it, I'll make it. I'm serious. So it's pretty straightforward. Well, that's the beauty of programming languages, though. When people, like, once you're speaking your programming language as fluently as you would your normal language, you can describe things extremely quickly. And so, like, I have a lot of experience using Shiny, trying to make dashboards for people to use, which usually people, from my experience, like, don't end up using them after a while. But if the community here thinks that it would be useful to have that, like, a free tool in place that they can just say, hey, I want a response surface design, I can do it in a matter of hours. If people want it, we'll do it. We'll figure out how to share it.
Yay!
Okay, I just bought myself some more work. This is good.
The other thing, if you do that, you send it and get some people here commit to doing it, and then you get some feedback on it to get it to it's really, literally almost a copy. It's super clear. It's easy to do. The only thing the person would have to do is load, I assume RStudio, that's a nice clean interface?
No, just do it in a web application. You'll just go to a link. It's like
Oh, just an
do it on
online
your browser.
compiler?
Yeah,
Yeah, that's, okay.
way easier.
Yeah.
You can do it on your phone.
Yeah.
You can do the whole thing on your phone.
Yeah, and just iterate back until it's super clear, and then just have a number of those modules for the different designs.
Yeah.
I think that could work.
I mean, if that's a tool people are interested in,
Yeah.
like it's not going to be hard to do. So if people are interested in it, I'll make it. I'm serious.
Let's create a community, and then we create a page, and then we can post what we want, and then Brett can help with that. If that is something we look for, that maybe we should think about create a community, DOE community. And we talk about that. Create some forum or something, right? Yeah. Okay.
But yeah, I know Doc.
Who the hell's here from that plant?
Yeah.
Say it again. I couldn't hear you.
Yeah, I was saying, would it not fit nicely with the plant gene community, what we were talking, or what you were talking about this morning, to be able to put this type of platform
Oh,
in
absolutely. Yeah. Yeah. I mean, but it seems like you've already started setting this up in SIVB links. So, but yeah, I think if we could have a section of plant gene that was kind of carved out for this type of interaction and for people to communicate about these methods, I think that would be fantastic.
The plan gene is open free to add all the membership, right?
Sure.
Okay, because SIVB, sometimes you have to be the SIVB membership to access something.
No.
If plan gene is open public, maybe it's more dry forum.
There are no requirements other than you
Yes.
just register on the site, and anyone can do it.
Okay, then we will connect back to you if we think, because we talk about that, how we make this more available to practitioners, more users. So maybe we'll connect with Plant Gene, and everyone interested in this one subscribe to Plant Gene, and then maybe we can step by step to build this forum, this community.
Yeah, I think that.
Yeah.
Thank you.
Thank you for the suggestion, and maybe we will have something in the future. So one last question or one last request before we close out today, because I think we like 25 minutes. So thank you, Steve, again for staying. Thank you for all the technical support back there. And one more question or suggest before we close out, or we can just close out right here, and then Brett and Randy still be around until Wednesday, I believe. And then if we have any questions, just look for them.
Yeah, so, yeah, Brett, maybe you and I, we can talk, get some basic designs. I mean, ones that are just very useful and routinely used, and then get some volunteers here. Okay. No, that would be a good one, because that one you're not going to vary much. It is what it is. Yeah. Get some people here to try it until they say, yes, this is clear, this is useful. Yeah.
Brett, we try to use the microphone so they can pick up on the...
And the roofs are high. But yeah, it's absolutely very possible. I know Dr. Neitz at one point published his ARS media spreadsheet at one point to help people with the conversion of ions to salt. I mean, I think us as a community, if we have these tools in place to make people's jobs easier, and so you can just look something up and it's free, and you can get into the analysis without having to convince your boss you need $1,000 to learn some new technology. I think that'd be a good thing. And realistically, it's not a lot of work at all. It's pretty straightforward. If there's an interest in it, I have no problem writing it out.
Thanks, Randy and Brett again, and we will sign you up for lifetime member for DOE. So just be ready. Thank you, and yeah, good night, everyone, and see you tomorrow.